Hi, welcome back to the lecture series on Media Theory with course code MMTC 202. Today in this lecture, we will discuss integrable functions. Before discussing integral function, we'll first see that the collection of upper functions is not a vector space. Okay, collection of the the collection of upper upper functions is not a vector space. The collection of upper functions is not a vector space. So for this, we take the following function. Define a function f. Define f from R to R by define this f by f of x equal to 0. If x is not in this interval 0 to 1, outside of this interval, its values of f are 0, and it's equal to and f of x is equal to root of n if x belongs to the interval 1 by n plus 1 to 1 by n. Okay, so semi-closed interval. So this is the function f which takes the value 0 outside of this interval. Okay, and if its value is equal to root n for x belongs to 1 over n plus 1 to 1 over n on this interval. So suppose for n equal to 1 on the interval 1 by 2, for n equal to 1 on the interval 1 by 2 to 1, the value of the function is root of 1, and say for n equal to 2, the f of x equal to root 2 for x belongs to 1 by root 1 by 3 to 1 by 2. So that's the definition of, and you see this function is not a bounded function from the upper side, from the above side, because whenever x is approaching to 0, whenever n is approaching to infinity, this will be an unbounded function. But we will see that this function is an upper function, and we will see its integral also exists. Okay, we show that f is an upper function. We show that f is an upper function. So for this, we have to show that this f has a generating sequence. So let's define this first sets for that generating sequence. Put ak equal to the set 1 by k plus 1 to 1 by k. Let's take this set. Then the Lebesgue measure of this set is Lebesgue measure of ak is equal to the length of the interval. It's an interval. It's 1 by k minus 1 by k plus 1, and which is equal to 1 by k into k plus 1. 1 by k into k plus 1. That is the Lebesgue measure of this set. Now define the step function. Define phi k, which is equal to summation k runs from 1 to n root of k into characteristic function of a k. Then this phi k is a sequence of step functions because the Lebesgue measure of each set, each ak is finite. Then this phi k is a sequence of step functions. It is also increasing and such that this phi k, it increases to f for all x, for all x. Also, this integral of these step function is that this integral is equal to, it's very simple, you can easily calculate. You have to verify this also, this limit is equal to f, verify it, okay. And you also verify this integral of phi n, it's k runs from 1 to n, k runs from 1 to n, root of k into the Lebesgue measure of the set AK, that's equal to 1 by k into k plus 1. So which is equal to summation k runs from 1 to n, 1 by root of k into k plus 1. And you can see this series, because the power of the k in the denominator is greater than 1, it's 1 plus 1 over 2, so this series is convergent, okay. So that means there, it's easily, then this implies the limit n approach to infinity, the integral of phi n, which is equal to the series k runs from 1 to infinity, 1 by root of k into k plus 1, which is finite. So therefore, this phi n, therefore phi n is a generating sequence, is a generating sequence for f, and hence f is an upper function, and hence f is an f is an f is an upper function. And not only this, and we can also have an integral of f, which is equal to the limit of, by definition, which is equal to summation k runs from 1 to infinity, 1 by root of k into k plus 1. So this is an upper function, but you will see this minus f, but minus f, which is equal to 0 for x, is when x is not in the interval 0 to 1, and its value is equal to minus root of n for x belongs to the interval 1 by n plus 1 to 1 by n. Okay, this here closed interval, this is closed interval here. Okay, and this function is not bounded below, because whenever x is approaching to 0, this will approach to minus infinity, minus f. So therefore there does not exist a sequence phi n of step functions of step functions of step functions such that phi n increases to f by minus f. Because whenever suppose we have a sequence of step functions such that phi n increases to minus f, then each phi must be less or equal to minus f. But phi n's are bounded functions, bounded below functions, they are bounded in fact, they are bounded functions. So we don't have any step function phi n such that phi n is less or equal to minus f, as minus f is not bounded below. Okay, so for if there is a step function phi n such that phi n less or equal to minus f, then minus f must be bounded below, but minus f is not bounded below, because as this n is approaching to infinity, minus f is approaching to minus infinity. So we don't have a sequence of step function with this condition that phi n increases to minus f, because this condition means that phi n must be less or equal to minus f. So therefore minus f is not an upper function. Therefore minus f is not an upper function. So thus collection of upper function is not a vector space, because f is an upper function, but minus 1 times f is not an upper function. It's not closed with respect to scalar multiplication. So to overcome this problem, we discuss now a collection of integrable functions which will form a vector space. So we define the collection of, we define integrable function now. Okay, integrable functions. integrable functions. Integrable functions. We discuss now integrable function. Now we discuss integrable functions. Okay. So first we define integrable function. A function, a function, a function f from x to r is said to be an integrable function. Is said to be an integrable function. Integrable function if there exist two upper functions. Two upper functions u and v. If there is two upper functions u and v such that f is equal to u minus v. If a function f is a difference of two upper functions, then that function is called an integrable function. But this equality is almost everywhere. And we define that the Lebesgue integral of f is defined by the Lebesgue integral of f is defined by integral of f is equal to integral of u, which is already defined, integral of an upper function minus integral of v. So that's the definition of integral of an upper function. Integral of an integrable function. It's equal to integral of u minus integral of u v, while integral of u is already defined, integral of v is also already defined. So both are finite. That means difference is finite actually. So this is the definition of an upper function, and now we'll see that this integral is independent of the choice of the representation of an integrable function, because the integrable function f may have two representations as a difference of two upper functions. So you say suppose f is equal to u1 minus v1, and the same f is equal to u2 minus v2. Now we'll see that. Now we see that the integral of an integrable function f is independent of its representation as a difference of its representation as a difference of two upper functions. So suppose we have two representations. Say f is equal to u1 minus v1, which is equal to u2 minus v2, where u1 v1 u2 v2 are upper functions. Now let us see this integral of f. It's equal to integral of u1 minus integral of v1 when it can be represented as a difference of two upper functions. But when we represent this as a difference of two upper functions, it's equal to integral of u2 minus integral of this is This is correct. Okay. So this is here when it's represented as difference of two upper function u1 minus v1, then in that case it's equal to this. So okay, it's not correct. It's not the way of doing this. So it's this implies it will be u1 plus v2 u1 plus v2 is equal to u2 plus v1. Now we apply the integral. Now we have only positive this is plus okay. This means integral of u1 plus integral of v2 is equal to integral of u2 plus integral of v1, and this implies integral of u1 minus integral of v1 is equal to integral of u2 minus integral of v2. So that means the integrals are the same. So therefore integral of f is independent of its representation as a difference of two upper functions. And one more thing, if f is an integrable function, if f is an integral function, and this f is equal to g almost everywhere, then g is also integrable. Then g is also integrable, and the integrals are same. Integral of f is equal to integral of g. So that's very simple that you verify yourself. Okay. Now we can see this collection of all the big integral functions a vector space. It is also a function space. This vector space is very simple now because now it's closed with respect to scalar multiplication. So that's an exercise. Show that the collection of all integrable functions, all integrable functions is a vector space. Now you will see that if f is vector space, then minus f is also vector space. That's not simple. That you can easily verify. If f has a different, if f is represented as a difference of two upper functions, say u minus v, then minus f is represented as v minus u. So minus f is also an integrable function. Also show that it's a function space. It is a function space. Function space means you need to show that if f is an upper function, g is an upper function, then f plus is also an upper function. And in fact, you will see this. If f is equal to u minus v, then you verify this f plus is equal to, which is equal to u minus v plus, and you can see this is equal to, you verify this. It's very simple. It's u join v minus v. This is u join v, okay? U join v. This is join here. This is join here. U join v. So join of two upper function is again an upper function. V is an upper function, so it's again difference of two upper functions. So that means f plus is an upper function. You verify this equality only. Okay? This equality, this one. You need to verify this one. So that's this forms function space. Okay. Moreover, if f is an upper function, then mod of f is also if f is an integral function, then mod of f is also an integral function. So this exercise is show that if f is an if f is an integrable function, if f is an integrable function, then mod of f is also an integrable function, is also an integrable function, and also it follows from the previous theorem that f is Lebesgue integrable. From previous exercise, in fact, you can see where we have seen that f plus is equal to u join v minus v, that means whenever f is an upper function, then f plus is an upper function, integrable function, sorry. If f is an integral function, then f plus is an integral function, and from this you can conclude that so from the previous also we have this f is equal to f plus minus f minus, but whenever f is an integral function, then f plus is an integral function. So this implies f is integrable. F is integrable if and only if f plus and f minus are integrable. This is now simple. Why? Suppose f is integrable. Then by previous exercise, f plus is integrable. So from this equation, now what will be f minus? F minus is equal to f plus minus f. Since f plus is integrable, f is integrable, so that means f plus minus f is integrable, which is equal to f minus. So which means that f minus is integrable. So that means whenever f is integrable, then f plus is integrable, f minus is integrable. And conversely, if f plus is integrable, f minus is integrable, then their difference is integrable, but their difference is equal to f. So that means f is integrable. So that's now 10. Okay. Now we have some properties of integrable functions. That's in this theorem. If f and g are two integrable functions, if f and g are two integrable functions, are two integrable functions, then this alpha f plus beta g is also that's trivial, and but this integral alpha f plus beta g is equal to alpha times integral of f plus beta times integral of g. Okay, for all alpha beta belongs to the real numbers R. So this is very simple. This is very simple. This is integrable. It's simple, and the integral is equal to this one. So let me do this. Okay. So suppose our f is a difference of these two upper functions, and g is equal to difference of these two upper functions. Okay. So then integral of f is equal to integral of u1 minus integral of v1, and integral of g is equal to integral of u2 minus integral of v2. Okay. Now alpha f. What's alpha f? Alpha f is equal to alpha u minus alpha v1. Okay. Suppose alpha is positive, then alpha u1 is upper function, alpha v1 is upper function, and if alpha is negative, if if alpha is negative. So for positive there is no problem, because positive multiple of upper function is an upper function, positive multiple of upper function is an upper function. That's trivial. But if alpha is negative, if alpha is less than 0, then what's alpha f? Then can we express alpha f as a difference of two upper functions? Yes, we can do it, because we can write this alpha f is equal to minus alpha times u v1 and minus alpha times u1. Now here minus alpha is positive because alpha is negative. So it's positive times upper function, which is an upper function. It's positive times upper function, which is an upper function. So that again it can be expressed as a difference of two upper functions. So which means alpha is an integrable function. So similarly, so that there this means alpha f is an upper function, is an sorry, not upper function, is an integrable function, is an integrable function, is an integrable function, is an integrable function. Similarly beta, similarly similarly beta is an integrable function, is an integrable function. Now we take the case if alpha is greater or equal to 0. Now assume alpha comma beta are greater or equal to 0. Then this alpha f, which is equal to alpha u1 minus alpha v1, and beta f is equal to alpha beta u2 minus beta v2. Okay, beta v2 minus beta beta v2 minus beta u2 minus beta v2, which implies what will be alpha f plus beta g, which is equal to alpha u1 plus beta u2. This is an upper function because sum of two upper functions is an upper function, minus times alpha v1 plus beta v2, which is again an upper function, and this implies what will be the integral of this alpha f plus beta g. It's equal to integral of this function alpha u1 plus beta u2 minus integral of alpha v1 plus beta v2, and that's equal to, you can see this is now simple, because for upper function we can move out this scalar. That's simple. So what to do here, it will be alpha times integral of u1 minus sorry, alpha to integral of u1 minus integral of v1 plus beta times integral of u2 minus integral of v2. You can easily verify this, and this is equal to alpha times integral of f plus beta times integral of g. So that proves this theorem. Now in next theorem we will see that every integral function f which is non-negative is an upper function. So every non-negative integrable function is an upper function. Every integrable function need not be an upper function. That's simple, because as we have seen that a function f which is an upper function, therefore integrable function. But minus f is not an upper function, and minus f is an integral function. In our example, we have seen an example of a function f such that f is an upper function, but minus f is not an upper function. So since f is an upper function, therefore f is integrable, which means minus f is also integrable, but minus f is not an upper function. So that means integrable function need not be an upper function. That's the case. So one thing that you should note, that every upper function is an integral function, because if u is an upper function, then you can be written as u minus 0, u minus 0. You can be written as u minus 0. Then this u can be written as u minus 0, which is again which is the difference of two upper functions. Therefore, every upper function is integrable, but converse is not true. But converse is not true. And converse is true when this integral function is non-negative. That's this theorem. If f is an integrable function, if f is an integrable function, if f is an integrable, if f is an integral function such that this f is greater or equal to 0 almost everywhere, then f is an upper function. Then f is an upper function. Every non-negative integrable function is an upper function. And I will do the proof for you. The proof is it's the theorem number. The proof it's theorem number 22.4 on this elements. Okay, elements. So you will see this proof. It's at page number 168. If you want to see the 168, okay, you see this proof. Every non-negative integrable function is an upper function. So from this theorem, we conclude that now we have enough standard representation of an integrable function as a difference of two upper functions. We know that suppose f is integrable. From this, you can conclude the following from this theorem. Suppose f is integrable. Also, this f can be written as f plus minus f minus. Then this f plus and f minus are integrable, because we have seen that f is integrable if and only if f plus and f minus are integrable, and also they are non-negative. This is greater or equal to 0, f minus is greater or equal to 0. So f minus and f plus and f minus, they are integrable and non-negative function, which implies that f plus and f minus are upper functions from by the previous theorem of upper functions, and this f is difference of these two upper functions. This is the standard representation of f as a difference of two upper functions, and the integral of f is now equal to integral of f plus minus integral of f minus. So this is very nice nice equation. This f can be written as, this is the standard representation of f as a difference of two upper functions, because f plus is upper, f minus is upper, and the integral of f is equal to integral of f plus minus integral of f minus. Okay. So the next theorem is the next theorem is if f is an integrable function, 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 then for each epsilon positive, the measurable subset has finite measure. The measurable subset of x, obviously x belongs to x such that mod of fx is greater or equal to epsilon. For every epsilon positive, this has a finite measure, has a finite measure. F is integrable function. Then for each epsilon positive, this subset of x has a finite measure. proof. Now, first we fix epsilon positive. Fix epsilon positive number. Let's take this set. Let A be the set x belongs to x such that mod of fx is greater or equal to epsilon. So we'll see that the measure of this set is finite. Now note that epsilon times the characteristic function of A is less or equal to mod of f. This is very simple. Suppose x belongs to A. Suppose x belongs to A. Then this side is equal to epsilon, and this side is less or equal to epsilon. This side is greater or equal to epsilon, because whenever x is in A, mod of fx is greater or equal to epsilon. So this is greater or equal to epsilon, this is equal to epsilon. So therefore this inequality holds, because for x equal to A, we get epsilon less or equal to mod of f, which is true whenever x is in A. If x is not in A, then this is equal to 0, and which gives mod of f is greater or equal to 0, which is always true. Mod of f is always greater or equal to 0. So in both the cases, whether x is in A or x is not in A, this inequality always hold. This inequality always. So that means epsilon times the characteristic function of A is always less or equal to mod of f. Okay. So now we can see this now this function. Take this function. Now the function 1 by epsilon times mod of f is an integrable function, because it's the scalar multiple of, because f is integral, mod of f is integral function, is an integrable function, is an integrable function. So this function is an integrable function, and it is also non-negative. Also this implies 1 by epsilon times mod of f is an upper function, because it's non-negative, and integrable is an upper function, is an upper function. So whenever it is an upper function, then it has a generating sequence. Let's take this generating sequence. Let phi n be generating sequence, for be generating sequence for 1 by epsilon times mod of f. Then you see, then this sequence phi n meet characteristic function of A is a sequence of step function, is because this phi n is a step sequence of step function. So phi n meet any simple function, whether it's not, if it's not, it's chi a is a simple function, it's not a step function in general, but it's the meet of a simple function with step function is step function. Okay, is a sequence of step functions, is because it's the minimum of these two, is a sequence of setup, is a sequence of step functions, such that this holds phi n meet characteristic function of A. It increases to, because phi n is increase, it increases to characteristic function of A. Why? Because phi n increases to, you can see, because as phi n increases to 1 by epsilon times mod of f, because phi n is a sequence of step functions for this function, but this one and this one is lesser, and 1 by epsilon times mod of f is greater or equal to chi of E. Okay, it is here, this is greater or equal to chi. You can see it at this page number. Here you can see this. So 1 by epsilon times mod f is greater or equal to chi of E. So what will be the minimum of chi of A and 1 by epsilon times mod of f, which is equal to chi of A. So that's why this limit is here this limit is here chi of A, because the limit of this is equal to 1 by epsilon times mod of f, and chi remains the same. It's independent of the limit. So the limit of this is equal to the mean of 1 by epsilon mod of f and chi of A, and which is equal to chi of A, because chi of A is less or equal to 1 by epsilon times mod of f. So this is this secant subset functions increases to chi of A, increases to chi of A. Thus, 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 we have this mu star of A. It's done in our one of our lecture. Whenever certain secant subset functions increases or secant subset functions increases to the characteristic function of certain set, then measure of that set is equal to the limit of the integral of this. It's equal to limit and approach to infinity integral of phi and meet chi of A, and this is a less or equal to this one. It's less or equal to, it's less or equal to limit and approach to infinity, limit and approach to infinity integral of phi of n, because phi of n is greater or equal to the meet of phi of n and chi of A. Okay, d mu, or cannot, you don't need to write here d mu, it's understood here. And this one limit of n, it's equal to 1 by epsilon times integral of mod of f. Okay, because this phi n is the generating sequence for this function. So the limit of the integral of that phi n will be equal to the integral of this function, integral of 1 by epsilon times mod of f, which is equal to 1 by epsilon times integral of mod of f. And this is finite, because integral of f is finite. F is an integral function. Mod of f is an integral function. So which means that mu star of A is finite. That is the theorem, because this what we have to show actually. This is because this set A is the set where x belongs to x, such that mod of fx is greater than equal to epsilon, and in our in this theorem we uh, uh, we have to show that the measure of such a set is finite, and this is the set A actually. That set was A. Okay, this is the notation for the set, for that set. If you want to see here at the beginning of the theorem, this is the set A. We have to show that this measure of this set is finite. Okay, this set, and this set is denoted by A. So that means we have to show that the measure of the set A is finite. That's what we have shown here. Measure of the set A is finite. So this proves the theorem completely. Okay. The next theorem is let f be a measurable function. Let f be a measurable function. This is also very important theorem. We will use this theorem in our coming lectures. Let f be a measurable function if there is two integral functions. If there exist two integrable functions g and h, such that g less or equal to f less or equal to h almost everywhere, then f is also integrable. Then f is also an integrable function. Then f is also integrable. So a measurable function lying between two integrable functions is always integrable. But the condition is that f should be measurable. If f is not measurable and it lies between two integrable functions, then f need not be integrable. But whenever f is measurable and lies between two integrable functions, that must be integrable, and its proof is not too difficult. I will leave it for you. Proof of this theorem. So you can see the theorem number 22.6 on L prints. And if we want to see the page number, we want to this page number of this theorem, its page number is 169. Okay, you will see this proof. It's a two-line proof only. You can see it. Okay, one more theorem that's again a simple that I want to leave for you, which is for integral functions f and g, the following, this is a property of integral functions. For integral function f and g, for integrable functions f and g, the following hold. First property is integral of mod of f is equal to 0 if and only if f is equal to 0 almost everywhere. And second is if f is greater or equal to g. If f greater or equal to g, this is very simple. This implies integral of f is greater or equal to integral of g. We have proved these results for upper functions. You can apply those results because f is integrable, therefore f is the difference of two upper functions. Okay, then you have to transfer those upper functions so that this positive sign will remain there. So that's very simple. You can see it. And this one, integral of f d mod of the integral of f d mu is less or equal to mod of is just an integral of mod of f d mu. This result you have already proved for Riemann integral functions. Mod of integral of f is less or equal to integral of mod of f. Okay. Now you have to prove this result for integrable functions also. So again, you can see these proof yourself. The proof is the theorem number 22.7 at page number 169. Okay, theorem number 22.7. So I will leave the proofs of these two theorems for you, so you can easily do these because they're not too difficult. In the next theorem, in the next lecture, we will see the Levy's theorem, which is very important in this course, and then we will see Fato's lemma. Then we have Lebesgue dominated convergence theorem. We have monotone convergence theorem. So we have some named results of for this. We'll see those results in our next lecture. Okay, in our next lecture, we'll see these results. Thank you.